here for visiting his relative, so we think it's a good opportunity for us to invite him to come here to give a talk on some exciting topic. He has been working on quantum computing, information, and also condensed matter physics. But today he will focus on a publication he recently did, focusing on quantum chaos, basically spatial-temporal volume entanglement. Please go ahead.
Thank you so much. Yeah, I'm visiting my family. My brother lives here, and I just randomly dropped an email to Professor Gang Shao, and he was kind enough to invite me. So I'm based at Monash University, but I'm on leave from Monash. I'm working at Transport for New South Wales, which is maybe a strange thing to see, but Transport has recently invested in trying to figure out what quantum computers can do for logistic problems in the long term. So we're just exploring it. So here we're really thinking about what can we do that is useful with quantum computers. But at Monash, I usually work on things having to do with noise in quantum computers, and so we're trying to make quantum computers better. Chaos stuff happens in free time, and so that's kind of a hobby, if you will. That's not what pays the bills. Monash is in Melbourne. My transport job is in Sydney, and I live in Queensland, which is yet another state. So it's like working in New York and Chicago and living in Florida, just to make life more interesting. Okay, look, I'm going to talk about these ideas of chaos, but I'm going to build up to that with some work that we did on quantum stochastic processes. And feel free to stop me. As usual, there's probably too many slides, so I probably won't finish. But I would be very happy to have a discussion along the way and explain things properly. So I want to start by talking about classical stochastic processes and what we mean by that. So imagine that we have some stock that we're trying to determine what its price will be next week. So there's a possibility that it will oscillate between $20 and $14 over the next week. And there's also a possibility that it will go up to sorry, you have to read this backwards, right? Go up to $30, then oscillate between 24 and 30, and then drop down to $11. Now, there are of course many other possibilities that I haven't listed, and a classical stochastic process is the joint distribution of some random variable, which is the price of the stock, over time. So it's all the possible values the stock can take. Now, most of them, the probability for most of these things is going to be zero, but there will be some significant fluctuations in possible prices that we might care to describe. Now, one of the features that classical probabilities have is that suppose you don't care about what the price is on Wednesday. Well, what do? You can just trace over. You can average over all possible prices on Wednesday, and you can get the probability distribution for Monday, Tuesday, Thursday, and Friday by just summing over all the values on Wednesday. It turns out that, this is kind of a obvious property that probability distribution have. That turns out to be quite annoying in quantum mechanics, so we'll get to that. And there's an idea called Kolmogorov extension theorem. What that says is that this joint distribution, this finite distribution of over 5 days, is actually coming from some continuous distribution that we can think of as some physical process. It's actually fluctuating continuously, and from that we are sampling to get finite time distributions of a finite number of outcomes. And the classical stochastic process is exactly this distribution. So that's what we care about, and we want to get an analog of that in quantum mechanics. So we'll start with that, and then we'll work our way towards chaos. Okay, so why do we even care about this? Well, there are lots of processes that are stochastic and quantum mechanical. So, for instance, suppose we care about this blue physical object that is attached to this big red molecule. And we want to understand its properties, dynamical properties. And well, one thing we can do is we can somehow detach the blue portion from the red portion and study it in isolation. But that's not really studying this system in its natural form. What we really care about is studying the dynamics of this thing while it's attached to this red molecule, because that's where all the interesting physics and chemistry and biology is likely to happen. Well, what experimentalists would do is shine light on this object and see how it reacts. That's not an easy thing to do, but one way to do it is just hit it with a bunch of pulses and see how it reacts. And people did that some years ago. This is controversial, so I'm not advocating for quantum biology, but this is an example of a quantum stochastic process where people hit a photosynthetic complex with pulses of light, and what they saw in responses is wave-like oscillations. And so they claim that biology exploits quantum mechanics. I don't know if I believe it, but at least one should have the language to properly describe such phenomena with having a complete theory of quantum stochastic processes. And that was one of the motivations for developing these ideas. But not the only motivation. A second motivation is quantum computer. So in quantum computer, what we want to do is we have a bunch of qubits and we want to apply gates to those qubits. And by applying various gates, we're going to build up some complex quantum state. And by measuring that complex quantum state is going to retain information. And by measuring that, we're going to learn, we're going to solve some problem. But as you know, gates are never perfect. There's always some noise. And so these perfect gates in panel A are really an approximation of what happens here. So our unitary transformation or quantum gates, feel free to stop me at any point if any of the language or symbols are not clear. There's probably a big language divide, between various disciplines. So there's some interaction with an environment, and the gate is effectively a transformation that is not unitary. Usually we call it completely positive trace-preserving map, or CPTP dynamics, and we have some we have mechanisms for correcting that. But even this is an approximation, because why should the environment disappear after the first gate and then appear completely fresh for the second gate? What really happens in reality is that there's an environment that's just in the background. It's just doing its thing. And the total dynamics we can describe as a completely positive trace-preserving map 5 BU. But the second map, the second transformation, not only it's going to depend on the details of the environment, but it's also going to depend on the choice of the first gate. So there will be memory in time. And we'd like to be able to clearly describe processes like that where the system remembers its own past. This is called non-Markovianity, and there has been difficulties in describing non-Markovian processes in quantum mechanics. This is an experiment that we did some years ago, and we did show that there is some non-Markovianity in IBM. So the first IBM quantum computer that is publicly available. We've done more sophisticated experiments since then. I'm not really going to talk about that. We have a whole software kit that's coming out soon that can deal with all sorts of complex noise mechanisms now that we're working with folks at Sandia to put together a large package. Okay, so So how do we get to a quantum theory for stochastic processes? So I asked the question, how do we quantize stuff? And I don't mean in the canonical commutator sense. I mean in more crayon. How do you do things in a simple way with some hand wavy rule? So classically, we have things like probability distributions. The analog of probability distribution for quantum mechanics is density matrices in general, or it could be wave functions, either way. So that's what the classical probabilistic states are represented by wave functions or density matrices in quantum mechanics. So let's say I have 3 coins, and they may be correlated, they may be independent. Now, if I want to take those 3 coins and turn them into quantum systems, what I would do is I would write down a tripartite density matrix. It could be 3 qubits, 3 two-level systems that are correlated with each other. But what we really want to do is transform a probability distribution of a single variable over time. So we just have 1 coin, and that 1 coin is being flipped 3 times in a row. And that is described by the different outcomes that we get in a sequence is described by this probability distribution, and we'd like to have a density matrix of a single quantum system over many times. And that is not so straightforward. So why is that? Well, let's consider generic quantum dynamics. So the U's here are unitary transformations, so that's equivalent to Schrodinger dynamics. But I want to consider a situation where I have a system S interacting with an environment, and I don't have access to that environment. That is something I can't touch. The system I can measure, or I can apply unitary gaze to the system. I can manipulate the system however I choose. Environment I can't do anything about, and I don't know anything about the background dynamics that's in red. All right, so now, formally we call these A's completely positive maps. They're not necessarily trace preserving, so they could can account for unitary processes. They could account for measurements or something in between as well. And the language often is used. They're called instruments. An instrument is a collection of completely positive maps that adds up to something that's trace preserving. The label X denote the outcomes of an instrument, and the subscript denotes the time at which in the sequence. So suppose we were to we apply a sequence of instruments to our system, and we get some final state, and we measure that with some measurement operator. And we take the trace, and we get a probability distribution that looks exactly like classical stochastic process. We just have a bunch of different outcomes over time. Right? So can this be a good definition of a quantum stochastic process? The answer is no, and here's why. Suppose I run the experiment on top, where I apply various instruments at time 0, time 1, and at time n-1, and all the way to the end. And then I do exactly the same thing, but at time 1, I don't do anything. I don't apply any instrument. I just let the system be. Okay. So I don't make a measurement. So now, can I get the bottom case from the top case by summing over all of the outcomes at time 1? Think about it this way. Suppose you do a Stern-Gerlach experiment, and you do a Z measurement. And then you said that, no, I don't actually want to know what the outcome was. I'm just going to ignore it. Is that the same as not doing the Z measurement? So I've been living in Australia for too long. I start saying Z now. But I spell everything with S's instead of Z's. So it's a mess. The answer is no, right? Because not doing something is not the same as averaging over the outcomes in quantum mechanics. And that's a problem, because that breaks down the Kolmogorov extension theorem that classical stochastic processes must have. So what we really get here is we get infinite classical stochastic processes coming from these quantum experiments, where the infinity comes from the fact that we can choose arbitrarily large number of instruments, which instruments are just collection of these measurements or transformations. So there doesn't seem to be a well-defined notion of quantum stochastic process, because we get lots of probability distributions, and they not only depend on what's going on in the process, i.e. the unitaries and the state of the environment, but they also depend on what we decide to do. Right? We can't separate out our own choices from what's happening in the background, so it seems. But actually we can. So what I've done here, what I would like to do here is take this same process that I had in the previous slides, and I'm just going to move the control part, the blue stuff, the stuff that the experimentalist can do, or these are the gates that you would make on a quantum computer. I'm just going to move that down. I haven't done anything, I've just stretched the wires. Now I'm going to take my blue and red crayons, and I'm going to color the stuff on the top and stuff on the bottom. Okay. And that is the solution. The stuff on the top is nothing more than some big matrix with lots of indices. You can think of each of these wires some index of a matrix. It's a tensor, right? It's a multi-dimensional matrix or a tensor. And the stuff on the bottom is exactly the same object flipped upside down. And the relationship between them. So imagine you have some multi-time observable that we can call control operation A, and we define the tensor in red as upsilon. The expectation value of this observable is nothing more than the trace of these two objects multiplied together. They're just multidimensional matrices. So this is nothing more than the Born rule in quantum mechanics, right? It's just taken. So Born rule is just a fancy way of saying that how do you compute expectation values in quantum mechanics? Well, you take the density matrix, you multiply the observable, and you take the trace together. Or you sandwich it between Ra and the ket. It's the same. And what that does is it allows us to update the mathematical statement that we had. We have a sequence of random variable outcomes over time, given a choice of instrument. So given the A, and we can get all of these probability distributions if we know what that tensor, process tensor is. So if you can write down what that big tensor is, then you can compute expectation value for any control operation. And it turns out that you can experimentally construct it. It's a well-defined object. It's a finite number of experiments that you require, and so on. And it is this quest. We wanted to quantize a classical stochastic process and write down a density matrix of a single system over time, and that's exactly what that is. All right, so the reason for doing this is that we wanted to characterize complex noise, non-Markovian noise in quantum computers, and we've been able to do that. We can control it, and we can get, and I'm not going to talk about these things, but it's worth stating that we can get fidelities of 99% and more, only limited by shot noise, in characterizing complex noise. And that beats state-of-the-art techniques that don't account for non-Markovian noise. And then we can prove that this is a universal object. It is a quantum stochastic process, and it has nice properties, and so on. And for those in the audience that care about mathematical frameworks, this was there's a lot of activity in the community using formalism called quantum combs. What I want to talk about briefly before I move on to chaos is something that now we're calling many-time physics. So it is an analog of many-body physics. So in many-body physics, you might imagine you have a spin chain or a lattice of spins, and you want to talk about its ground states, for instance, or its excited states. So you write down a spin chain, and you can write down the Hamiltonian. You can compute its ground state, and various phases of matter correspond to different entanglement properties of those ground states or excited states. So the class of states that one encounters in many body physics is spatially entangled states that can be arbitrarily entangled, or you could have some things that can be classically handled, like tensor network states, or even something simple like separable states. And there are different phases of matter associated with these different entanglement structures. Now, what we have done is actually mapped quantum processes to density matrices. I haven't shown you all the details, but there is an isomorphism between the type of states you have here and the type of states you have here, modulo causality conditions. Quantum processes must be causal. The past cannot be affected by the future. And these processes have same type of entanglement structure as quantum states. They're just as rich, even though it's a slightly smaller set, but they're just as rich. And so there is a lot of interesting physics to be done here that we call many-time physics, and we're starting to explore different phases. So just to give you an idea of the type of things you can do is, so for instance, we're looking at the quantum bio study that from 2006. We're looking at that in this formalism. I called it chemistry because everything else starts with C, so I figured I call it chemistry. We're also looking at complex noise in quantum computation, where we have power law noise that you cannot truncate, not easy to deal with. And this is an ansatz that we've come up with. And then there are all sorts of interesting questions about causality. So you think about Wheeler's delayed choice experiment, where you put a photon through an interferometer, and on the other end of the interferometer, you decide whether you're going to measure in the wave sense or you're going to measure in the particle sense. And the particle somehow still knows, right? That the photon or the object that enters the interferometer knows what you're going to do, even though you haven't made the choice. You can construct a delayed choice experiment in the causal sense in these frameworks. It's a very rich structure. And what that means is that you start a process, and towards the end, you decide whether the communication goes from, say, Alice to Bob or from Bob to Alice. And that choice can be made once the experiment has started. So it's an exact analog of delayed choice, but in the causal sense. So you can change the causal order as you like. And then finally, complexity. So these processes we've shown that they are, in fact, complex, and in the computational sense, they're hard to classically simulate. And so what I'm going to talk about is the chaos stuff, and it comes from the fact that there's non-trivial entanglement structure in these processes. So now we've moved to chaos. Happy to, again, be interrupted if there are questions, comments. Yeah?
So maybe you're getting to this, Kavan, but is the entanglement stronger in the many-body particle sense versus the many-time sense? Or would we just see all ranges of entanglement in both situations?
Yeah, that's a good question. I think it is a bit stronger. It depends on the setting. So if we're talking about entanglement of the object in red, the process tensor, that object is not a pure, the density matrix of it is not a pure state. So we'll not have the full level of entanglement just by the fact that you've traced out something. But when we go to chaos, we'll actually retain the stuff that is traced out, namely this little stub at the end here. And then I believe it should be the same, but I'm not sure. I haven't really done a detailed study. Also, I'm not quite sure what, how you measure them, right? So, okay, so there's a rich history of quantum chaos, right? I mean, this topic goes back to goes back by decades, and we didn't want to we wanted to sort of start fresh, right? So we didn't really want to think about what previous things were said about quantum chaos, and we wanted to just ask the question, by what Lorenz was thinking. All we really care about is we want to have something small, some small quantum thing leading to some big changes in a big quantum thing, right? So a small quantum system drastically changing the state of a big quantum system. That's what we're going to call chaos, right? I mean, that's the spirit of chaos, right? That's the spirit of butterfly effect. And what I'll show is that we can actually capture all of the old notions of quantum chaos in this unified theory. So we're going to quantize this by putting a bracket around it. Okay, so here's sort of a one slide summary of what's out there. On left-hand side, we have mechanisms for chaos. So this is level spacing statistics. Level spacing statistics are strongly correlated with chaotic behavior, both classically and quantum mechanically. But there is no sort of proof, right? In fact, there can be violations here. Random matrix theory. So you take Hamiltonians with certain random structure and can have some relationship level spacing statistics, and they also lead to chaotic things. I haven't said what it means for something to be chaotic, but I'll get to that in a minute. Random circuits. Random circuits are also known to be chaotic. So now what does it mean? What does chaos mean? Well, that's on this side. So in terms of Hamiltonians, what we might think about chaos in terms of fidelity decay, as talked by Loschmidt and Peres. And the idea is that you have some Hamiltonian evolution versus you have Hamiltonian evolution with small perturbation p, and those two states at the end are going to be nearly orthogonal, and that's a notion of chaos. Another notion is dynamical entropy, where we look at the state of the system in time by measuring it, and if it looks like if it's just random the whole time at every time step in a sequence, then that may be chaos. This was something that Lindblad did in 1979. And then more recently, people have looked at things like out-of-time-order correlators, AUTOCs, and also before that, the notion of local operator entanglement. And we've actually shown recently that AUTOCs is a very special case of LOE, which is a pretty good measure of chaos. But so those two sides sort of existed. What we wanted was something in the middle that can bridge these things together. We want to know the structure of quantum chaos in this spatial temporal sense. What entanglement structure does it have? So, and then finally, it'd be still nice to have some more concrete relationship between quantum chaos and classical chaos. And we've got some results pointing toward that as well. Okay, so the tensors that I drew on earlier slides is a fancier formal way of saying calling that tensor, and it's called Choi-Yamelkowski isomorphism. And what it does is it takes a quantum process where you have a system and an environment, and you might do some things to a system. It takes that and it turns it into a quantum state. And the way it does that is by inputting half of a maximally entangled state at every time. And then you get a state at the end. That state is a pure quantum state. It's a spatial-temporal quantum state. This upper bit is purely a spatial degree of freedom. And this bottom bit is a temporal degree of freedom. It's a pure state. So in the density matrix sense, if you square it, it comes back to itself. And our thesis was that this state should contain information whether a process is chaotic. Now, this state is a function of nothing more than the unitary process and the initial state. And we'll be able to actually separate the two out. We'll show that it's really something about the way these unitaries are that leads to chaos. So we have three criteria that we can state in a formal way. So I want to first point out that we're calling the spatial part as we label it as R, and we label the temporal part as B. That's B for butterfly. Okay, so here are the criteria. We want the final state of R, of the spatial part, to be strongly sensitive to a butterfly. So we might imagine that R is a bunch of qubits, like 100 qubits, and B is a butterfly fluttering, doing its thing, single qubit. So B has many temporal degrees of freedom, R has many spatial degrees of freedom. We want the butterfly to affect a large part of R. So imagine we have a butterfly in here, and it's beautiful, and it does flaps its wing, and we all look at it and we'll go, oh, isn't that beautiful? Now, of course, butterfly can affect this whole room, but it's not going to cause a tornado out there, right? We want a tornado out there, otherwise it's not chaos, right? So we have to demand that it affects the whole system or something big, something extensive. And finally, different flutters of butterfly should lead to different enough states on R. And this turns out to have surprising connections with stuff that's happening in high energy physics, in black hole physics, where, for instance, Susskind has proposed that volume of a black hole is somehow related to complexity of the black hole. And this turns out to have a very similar situation. It's still murky. We don't fully understand all the details there, but there's a strong relationship. Okay, so how do we do it? Well, we have these quantum processes. We can ask the following question. We take two instances of the same process, and we consider two different butterfly flutters on the small system, which can be a single qubit. We call this X flutter and the Y flutter. And what we want is that because of these two flutters, we want the final state of R to be very different. Tornado on one side and nice sunny cloudy day like outside on the other side. Right? So we really want this massively different things happening just because the butterfly does something slightly different. So, well, we can write down that final state as nothing more than some initial state, unitary dynamics, and sandwiched between the butterfly's action, which we label as A. And then we normalize that state because we don't really care what the probability of the butterfly doing a particular flutter is. We just care that it's done a flutter. So given the butterfly's done some flutter, what happens? Okay, So now a little bit of algebraic manipulation. We take these processes, we apply the Choi-Yamilkowski isomorphism, and what that does is it takes the butterfly's action and turns them into quantum states that are coming in like that, and then we get conditional states on the rest. So this is just a graphical calculus of this exact condition. So in other words, this line is just comparing how close they are. Right?
This is probably a silly question, but am I correct in assuming that any when we do this combing procedure, there's going to be some entanglement between A and or B, like information between A and like E, say for instance, that's now going to be encoded in B?
Between A and E?
Yeah.
So what we're assuming here is that A only acts on S. A doesn't touch.
Or rather, there's going to be information between S and E that is
right.
that is changed by A, and that's now encoded in B.
That's right, exactly.
Okay.
So this might be an entangled state. Suppose you make a projective measurement. Depending on the outcome, this will, and you can also do a unitary. And given that unitary, the whole state will change. Then you have some dynamics, and then so that it's
the overall unitary of the S tensor E over the entire thing is preserved by, like, even though we're sort of pulling out this A stuff by putting it into B.
That's right.
Okay.
That's right. Okay, and then we can do a little bit more algebra, and we can do a singular value decomposition and rewrite this thing as a tensor network state, and then we can ask the question: if we take upsilon, break it up into V and R parts, then how big are the singular values connecting these? Right? And the size of those singular values is going to determine how strong the impact of this choice versus this choice is on this inner product. So it's the butterfly doing stuff in time that affects the spatial component. Okay, so that's the thing we care about. We write it down like that mathematically, and then so we define a zeta. The zeta is effectively this inner product given two butterfly flutters x and y, and the probabilities px and py are the probabilities of those flutters. Now it turns out that those flutter probabilities are 1 as long as the flutters are unitary. So if you just do unitary transformations, then you can apply any unitary you like by choice with probability 1. If it's measurement and different outcomes of the measurement may not happen deterministically. So this is fully deterministic. Then we're going to come back here with the correction in a bit. So this correction, so once we do that, what we might want to ask the question, how different are these two states of the rest? So in other words, if I get two orthogonal states of the whole system, are they the same with a trivial difference? So imagine two strings of numbers, right? One string is just all ones, another string is all ones except 1, 0. Now if you write them down as vectors, they're orthogonal. They're different. But they're very marginally different. It's only 1 bit. It's different. So we don't want to think of that as chaos. We want changes to be big. Okay, so now here's our first result. How am I doing on time? 10 more minutes, is that good?
Yeah, 10 to 15. Yeah.
Okay, good. I can do that, I think. So here's our first result. So suppose we want the butterfly flutter fidelity to be very small. Sorry, I think I might have skipped something important on the bottom here. I did. So if we work through the algebra here, then this butterfly flutter fidelity is nothing more than you take the full process, which is a pure state, and you're applying it with an object that is only on the butterfly space. So that's nothing more than just asking what are the off-diagonal elements in the basis xy of this reduced density matrix on the B space. So in the end, all I care about is the reduced density matrix of the full process. That's going to determine what's going to happen, almost. So then, if we want this reduced density, if we want this fidelity to be close to 0 for all possible butterfly flutters, in other words, for any two choices of x and y that are different enough from each other, we want the big system to be orthogonalized, then if x and y are different, they're orthogonal themselves, their representation is orthogonal, then we want this to be maximally mixed. In other words, that should be proportional to just the identity matrix. Now, when is the reduced density matrix of a pure state identity matrix? When it's maximally entangled. Right? So that's our first result. We need a whole lot of entanglement for this to work. A different way to think about this is nothing more than quantum teleportation. All the butterfly is doing is that it's teleporting its flutter into the environment. And that, for different flutters, the environment reacts very differently. And because it's spatial temporal, you can do deterministic teleportation. You don't have to do. In other words, an identity channel is just a teleportation from past to the future with probability 1. Okay. I won't go into the details because time is a bit low, but a corollary of this first result is that Peres and Loschmidt Echo, the Peres fidelity decay, which is something Peres did about 30 years ago, 40 years ago, it falls directly out of this idea. And the way to see that is in Peres's, Peres just puts a small perturbation on the Hamiltonian. You can trauterize that dynamics, and that small perturbation, it's just the inner product between those two perturbation matrices, and that may, the perturbation may be just an epsilon. The inner product might be just an epsilon off. But if you do this many times, k times, then for a large k, that becomes an exponential decay. That's exactly what Peres finds. So it falls right out. Okay. Now, a third result, this comes from our criteria 2. The first result was from criteria 1. Here what we're going to say is that if we write down this state in terms of, so we have the butterfly and the rest, we write that down as some left and right cut. So we have some many-body state, we write down left and right cut. The entanglement in that better scale linearly in the size of the smaller system for all bipartitions. Now that's sufficient, right? So if you have large amount of entanglement, so if you have volumetric entanglement, a volume entangled state is one where the entropy of any part, it goes as the log of the dimension of that part, the smaller of the two. Then that is enough to lead to maximally mixed marginal state, and therefore it will be chaotic. There are some caveats there that are listed here, but I'm not going to worry about them right now. You have to be slightly careful. And one of the corollaries of that is dynamical entropy. So dynamical entropy was something that was invented by Kolmogorov and Sinai in the 50s. And what Kolmogorov, his intuition was that for chaotic system, if you the classical chaotic system, if you compute the entropy by breaking up phase space into little sectors, and then you divide that entropy by the size of the sector and take the limit as k goes to infinity, for a chaotic system, that should not go to 0, even though you have pure dynamics on phase space. And that's exactly what happens, right? Because if this entropy is linear in k, then k's cancel, and as k goes to infinity, the entropy goes to a constant, right? So even though you have a pure process at some point. In other words, if you wait long enough, you always have Poincare recurrences, but you might have to wait forever. Okay, so, and now a corollary of that is that if you have an area law type entanglement, what that means is the largest Schmidt coefficient of this pure state goes as log of the dimension of some fixed value, d, one dimension. That so that won't be chaotic. In other words, your reduced density matrix will always have a very big eigenvalue or some big eigenvalue sector. And you can detect that relatively quickly. Now we have to do some fine tuning. So what we want is we want V to be maximally entangled with R. But there are 3 different ways it can be maximally entangled to R. Different constituents of V can be entangled with different constituents of R. It could be that you have this situation, but a small correlation across this. Or it could be that all of V is strongly entangled with all of R. Now, this is known as Bernoulli shift. And Lindblad, he did very similar work in 1979. And what he found was that he called this chaotic. And the reason why I don't call this chaotic is because every time butterfly does something, it affects only a small portion of the environment. It doesn't affect the environment as big. And so but all of these, the marginal state here is going to look maximally mixed. So we need to be able to separate that out. So what we do is, instead of making the cut on V versus R, we make a cut that is spatial temporal. We take some part of R and some part of V, and then look at the entropies on that. And it's very difficult to spoof that. And Lindblad's counterexample, the Bernoulli shift example, we can account for that. Okay, I am going to wrap up very quickly. I'm going to skip this last part. Well, maybe not. Maybe it's worth talking about it because it's so interesting in terms of black hole physics. If someone cares about that, so let's imagine that we have a volume entangled state here, right? And we, on a single site, we make a sigma x operation, and we get a second state that is also going to be volume entangled because we just done a local operation. Then it turns out that these 2 states will be completely orthogonal. So in other words, if I suppose you start with a highly entangled state and you just flip 1 qubit, then the whole state is orthogonalized. So what we can do is we can ask the question, well, given the conditional state of R given butterfly did X versus given the conditional state of R given butterfly did Y, how difficult is it to correct between the 2? In other words, suppose I have a tornado and a cloud and a sunny day. How difficult is it for me to transform one into another? Because, I mean, intuitively, imagine you have this situation. You have a nice sunny cloudy day with partial cloud. You have a very similar day, but you have a little gray cloud here. Technically, these 2 things are orthogonal. So the question is, how difficult is it for me to get rid of that gray cloud so that I have the same type of weather condition? Compare that to when I have a tornado versus a sunny day. That correction is going to be much bigger than that correction, right? This you could even imagine. You take a little tiny Cessna plane and right through the cloud, but this one, good luck doing that with your Cessna. Okay, so So then the final condition for chaos is that we want this correction between, if we want to make these two states the same, we want this correction. In other words, how do we impose that this quantity goes to 1 given some correction here? That correction for chaos should be very complex. And that's exactly analogous to Susskind's complexity equals volume. The idea is that the complexity of this object better be high, but it's unresolved. Okay, now once you do that, I'm going to skip all this. It turns out that you can differentiate between space and time by doing that. I'm going to skip all that in interest of time. But once you do that, you can actually talk about quantum chaos with a single perturbation at initial time. Now, first time you probably heard about quantum chaos, people say that there is no quantum chaos because quantum mechanics is linear. And if you do a single perturbation, let's say you apply a perturbation pi on some quantum state psi, you get psi prime. Pi could be some small unitary. Then you do some unitary dynamics on both psi and psi prime to get phi and phi prime. Then the overlap between psi and psi prime and phi prime is identical. It's of order epsilon. So there is no quantum chaos. That's the idea. But suppose we ask the question, what is the correction that I have to make here to turn the evolved state here into the evolved state here? So we impose that correction for any initial state should these two operators have to be the same. We do some rearranging, and that turns out to be something that was discovered or that was posited by Thomas Rosen called local operator entanglement. And this is a quantity that is well studied. And the entanglement of this tiny operator grows to something very complex, and that's what they call chaos. And that's exactly chaos due to some initial perturbation. So there is chaos due to initial perturbation. It's just you can't see it if you use fidelity as the metric. What you should do is use correction as metric. Okay, with that, and then we've also shown that Autark is just a special case of LOE, and LOE is a bit more substantial, and the Autark height needs to die.
So should we should all of our calculations of Autark be LOE calculations instead?
They're harder, but yes. So no, because they're harder. Okay, you can. I'm going to skip this. The analogy actually comes down to classical physics beautifully, and we'll skip that. And then you can also do a whole lot of stuff on single body chaos, but I'll skip that as well. So I just want to end. How much of this diagram have we clarified? Well, the answer is probably a lot because I drew the diagram on purpose, right? So it's post-selected. But we have a good indication of going. So volume entanglement here gives us a nice arrow to operational diagnostics. For both Loschmidt Echo, for all of these things, we can make that connection rather concretely. We can also, I haven't shown this, but we can also show that random circuits will lead to this behavior. We don't know how to connect this to random matrices, and we don't know how to connect this to level spacing statistics. It's there, but it's not quite quite done. We've also got some interesting connection to classical chaos in the sense that if you start with chaos as Lorenz's statement about something small affecting something big, then the spirit of it is preserved. Okay, with that, thank you.
Questions, Sean?
I'm curious about this slide that you gave on this similarity between many-body physics and many-time physics.
Yeah.
So, so if I think of a, let's find a slide. So if you think of the many-body physics in any, whether it's spin or electrons, you can have a situation of let's say a coherent state. And there, yes, we understand why individual flip of a spin actually does not really change the state, because there's a rigidity, phase rigidity associated with it. So there often is related to symmetry breaking, right? So because they are connected was protected by a broken symmetry. And so in the many-time physics, what is the equivalent of such a coherent state?
So
Especially coherent in the many-body physics. So this is a many-time coherence. Can you speak of such a thing?
Yeah. So we have these temporally entangled processes. So we have entanglement.
So we're talking about, let's say, some single degrees of freedom. Right?
We have a single degree of freedom over many times.
Yes.
And it's entangled.
Yes.
So it's self-entangled across many times.
Yes.
So
I can imagine a spin or electron get kicked by the environment to say time 1, kick to the left, time 2, kick to the right, but this kick is random.
Exactly.
And then somehow you said over time, this single degrees of freedom does not lose its coherence.
It will be self-coherent across many times. So if you look at, you might look at that electron over, say, 2 or 3 time steps. It may look like it's just it's moving randomly. But if you look at it over many times, it may look like almost a pure entangled state, something that is self-correlated. Now, that entanglement, that entangled state belongs to some topological phase.
Mm-hmm.
And if you just change one degree of freedom, if you apply some transformation at one side or 2 sides, you will not necessarily take it from one topological phase to another topological phase, right? There are infinitely many entanglement classes, and you can't go between 2 with small local operations. So it's a very analogous situation. It's going to be protected. And it shouldn't be surprising, because the states here are identical to the states here, modulo some causality conditions, which should not matter.
So what is the equivalence of this phase rigidity in this many-time physics?
It means that when you have entanglement across many times, you're going to have to do a whole lot of work in order to localize that information. It's going to look very noisy. So in other words, something that is chaotic or highly complex, it's going to be hard to control. It's going to require a huge amount of effort to do. But now, on the other hand, you might ask the question, can I make measurements that are macroscopic in time? In other words, the evolution time scale may be in picoseconds, but your measurements may be in microseconds. So now you have to go between those scales. We don't quite know how to do that, but we're getting there. But when you sort of bundle those together, you might get coherences back.
Any other questions? Brenda?
So you talked about the quantum circuits potentially having volume law entanglement. What would that correspond to physically? So I can imagine applying any unitary I want in a quantum circuit. But if I look at fermionic states, it's usually area law.
So random circuits. So,
Yeah. Okay. But like if I wanted to map that into a particle system, would you ever be able to do that?
I think so. So this is a hand-wavy explanation. So there's this work by Andreas Winter's group in 2015. What they show is that if you have 2 interactions, and so let's say you have an X-type interaction and a Z-type interaction, and you have a bunch of particles and they interact with either X or Z in some with those interactions happening randomly between any 2 constituents, then what you get is a T-design state. So it's something that mimics a Haar random evolution up to some approximate T-design state, so up to some moment. So now imagine you have you you have some gas and the particles have some broken symmetry, and so they might interact with two possible manners as they come and collide with each other. And then that should lead to something complex enough that the final state will be entangled, that when you look at the marginals of it, when you do statistical mechanics on it, it's going to look like it's coming from a statistical ensemble, even though you can do exactly the same experiment over and over and over. The statistics entirely come from entanglement. And it looks like it's coming from a hard random evolution or something that mimics hard random evolution.
Thank you.
You started your talk by giving a financial problem. So what is the relevance of quantum chaos to predicting the market?
Predicting what?
The market, stock price. Well, how can banks use your theory?
I'm not telling you. Yeah, I don't know. This is something I do wonder about. I mean, the idea here is to quantify correlations in time, in space-time. And if you could find trends in the market in both space and time, so in other words, let's say you look at some stock portfolio and then you see how it's behaving, and if there are correlations, then you can make money off that. But I don't know how. It's probably computationally hard. And I guess the question for me is that, do people already do that? Do they look at correlations in time?
Oh, definitely.
I mean, there's money to be made. So.
Okay. Any other questions? If not, let's thank Kavan again. Thank you very much.
Thanks. Next time, hope you have fun. Yeah, I don't know what next time I'll try to come not at an off hour, and I'll wrap another email.
We'll have quite a few students. How many faculty?
But this was a good crowd, so I enjoyed it.
Well, include faculty from other buildings. You got faculty.
Yeah.
Yeah, that's right.
I should have asked this before. Something. So I was thinking about the many times versus the many large distance scales. So the example that occurred to me is suppose you have superfluid helium, right?
Yeah.
And so that's spatially correlated over long distances. You actually have entanglement over large physical separation. So the claim is that if you could look at an individual helium atom at many different times, you would be able to see signatures of that entanglement.
I think so. So this is sort of why I was asking the question I was asking earlier, that the spatial correlation should manifest in time just as well. And this is one of the reasons why we have the ansatz that we have. We're trying to see how these correlations, like so in a spin-glass system or a phase transition many-body system, what does it look like in time if you do some dynamics around it? We don't know the answer. My guess is that it's going to have the same behavior in not only space and time. We did have some result where we find these power law decay in correlation, and when we look at the non-Markovian memory, it seems to have crystalline structure, kind of like the they haven't even written this up. Kind of like Wilczek's
Time crystals.
Time crystals. Yeah. For the scrutinies,
what was bothering me thinking through this question, which I didn't answer, is you can't, if this were actually superfluid helium, you can't look at a single atom over a long time because you're not sure its identity for a long time. You lose, because in distinguishability, you lose it. And so that's a fundamentally quantum feature of this problem, is that you couldn't do the experiment to study the long-time correlations for a single.
Potentially, you could throw in a probe in there, an impurity, and see how that couples to helium somewhat strongly, and then look at the correlations on that. So yes, you're right. I mean, you couldn't actually identify a single system, or you could look at if you have some large system, you make measurements in a particular sector, and you only so instead of doing a tensor product, you do a tensor sum type of break, and that could work. I don't know though.
Yeah, there's some trouble connecting. Once you do a local experiment, then you lose the ability to have information about the long things far away from that local environment. Is that not just in practice but in principle?
Yeah, so I mean, and that's a good question. So I didn't mention it. So in one of the so what we think is that the converse of chaos, quantum chaos, is not necessarily integrable. We think it's many-body localized. I don't like saying that because that's a controversial topic nowadays, and I don't know enough about it. The reason being that all of the correlations get trapped in a local area, and then the spatial temporal state should have area law. Now, something similar should happen in, like, say, your helium example, where your things are going to get trapped locally, but that locality is defined it's not strictly area law. It's something that grows logarithmically. So you should retain information that decays slowly.
Okay, all right. It's possible.
Possible. I don't know. Yeah.
All right. Well,
that's
thanks.
my guess.
Yeah, nice talking to you today, too.
Yeah. Thanks. That's great.
Thanks for dropping by. You have a question?
Yeah. Sorry to this is maybe a silly question, but when you say topological phase in time, so this is, I mean, my mind goes to like essentially an analogy of like of Berry phase, like so like the idea is that we can do the same game that we do with Berry phase in regular condensed matter system.
Yeah, it could be. I don't know. So by topological phase, I mean different entanglement classes. So like as the simplest example is, so you're familiar with G and Z state versus W state, right? These are two different entanglement classes, and you can't go between the two via LOCC. And they, I guess, belong to different topological classes. And when you go to more than 3 qubits, you get infinite number of these phases. So the idea is that you belong to one of these classes, you're not going to be able to go to another one via LOCC. So just doing some local stuff is not going to transform the process. So it's going to be robust, right? It's, as long as it's got some long length correlations. If it's the number of your size of your operation is going to have quantum coherence order of that coherence that he was talking about. Sean, was it?
Sean.
Are you at liberty to discuss or mention the group at Sandia? I understand if not, like I know that they can be. Sorry.
I think so.
Oh, okay. Well, no. The reason I ask is because I'm actually working with. I think this might be a different group at Sandia, but I think this is very relevant. So the stuff that I'm on is thermodynamics, quantum thermodynamics of classical reversible computing, but
Probably
expressed.
a different group.
Okay.
What
Okay.
was the?
Do you know Michael Frank at all? Okay.
So the group that I'm thinking about is led by Robin Bloom-Cahoot and
Okay.
Kevin Young, and
Okay.
they're not really at Sandia. They're kind of all over the place. But yeah, they the only thing they do is noise characterization and control. The thing that they call gate set tomography.
Right.
So.
Okay. No, it's not the same group, but I think they are very familiar with each other.
I'm sure they are. Yeah. I don't know what the internal relationships and structures are. So.
Well, part of the reason I ask is because I think the structure has a lot of relevance to the kind of calculation that we're interested in. I mean,
okay. What is that?
Oh, like I said, it's just like characterizing quantum thermodynamics of classical reversible operations, but expressed as quantum channels, basically. So, so the most immediate calculation that I'm working on is if you're familiar with Victor Albert's geometry of Lindbladian stuff. So the first step,
but I haven't read it.
the first I mean it's Lindbladian, right? So it's just the Markovian thing. So that's the first step, and we're like characterizing some of the thermodynamic properties of that. But then, I mean, this is going.
I think you're spot on. Yeah. And I have thought about this. I think in a way the problem. So the problem should be relatively simple, right? Because you just look at it at some coherent length, and then you can reformulate the problem. What's nice is that if you don't have this structure, and you think of non-Markovian processes in the usual Nakajima-Swanzik way, then it's a mess. You don't know how to deal with it. But if you do it this way, then you just write down the process sensor as big as you need it to be when you have a memory cutoff, and then you just take the log of the generator, and you can do the usual techniques. So
would it be all right if I'd be very interested in the slides and maybe like have follow-up questions because
absolutely.
This is very relative.
Yeah, absolutely. And
I'll send an email, but
please do. My email should be available online if not.
Which department are you from?
I am so this is I'm at the tail end of this thing. I have been with electrical engineering.
Oh, okay.
I'm switching fields for job reasons for the job market.
Okay.
So this is
School of Engineering.
Yeah.
Okay, because I haven't seen you in physics. So.
Oh yeah. So I'm a PhD student in engineering, but I do have a master's in physics, not from Brown.
Okay. Okay. So now you know each other.
Actually, we've met Carpor. We've met once before. Actually, you probably don't remember. This was in Brazil.
Meeting.
No, this was in Brazil a few years ago.
Oh yeah. No, I do kind of remember that. This was at, in Nepal.
Yeah.
That's right. I do remember that now.
So I'm also.
I had more hair back then.
I did. Thank you. Yeah.
That makes a big difference.
Yeah, I was interested, and so this is. I'm also interested in some of the black hole dynamic stuff.
Yeah.
So
I was just starting to think about that. So. Great.
Yeah. Thank you so much. I really appreciate it, and thank you for having me.
Yeah. Okay. Yeah. So thank you very much for coming.
Thank you very much for having me. I really appreciate it.
I wish I have more time, but I have two visitors,
That's okay.
collaborators here also at the same day.
It's okay. I'll drop an email much earlier next time, and I try to make a longer visit.
Next time when you're in Providence, and
Yeah.
we have a decent sized condensed matter physics with a lot of people interested in quantum.
Oh, that's beautiful because we'll hopefully have more condensed matter results by then, and it was a very productive morning talking with Rich and Brenda. So that was good.
I see the interest is there.
Yeah.
We also have a huge group in high energy theoretical physics in black hole.
Yeah, that's why I mentioned the black hole stuff, and hopefully we have more traction there in the future. But that's an really interesting topic.
Okay.
I wasn't convinced that there was a connection between black hole physics and chaos, but now I think there might be something.
Yeah, I think so. Yeah. Very interesting.
Yeah, great.
So thank you.
Thanks.
So nice meeting you.
Very nice meeting you. I really appreciate it.
Bye.
Bye.